Good afternoon, ladies and gentlemen. It's very pleasing to see so many of you here to this historic event. And by historic, of course, I mean the lecture of 2018 Nobel Prize laureate, Professor Gérard Mourou. Applause. Yeah, so this talk is actually to celebrate two parts. The first part is the inauguration of Professor Mourou to the foreign members of the Lithuanian Academy of Sciences. And the second part is a lecture of the Open Readings 2019 conference, which is held right across the street in the National Sciences and Technology building. So we welcome you to also come to our conference, and you can check the program at the openreadings.eu website. Yeah, so we have a lot of guests here, honorary guests, so I would like to give a word for them. So the first, I would like to ask the president of Lithuanian Academy of Sciences, Professor Juras Banys, to say a few words, please.
Maybe I will stand up. So, dear colleagues, ladies and gentlemen, and colleagues, I mean all professors, associated professors, and of course students. And a bit of history. In 2002, when I became a dean of physics faculty, Professor Algis Piskarskas was a chief of student conference. You remember this time, for sure. And in 2003, it was, or 2004, it was the idea to make the conference international student conference. And what I see today, I'm very glad that this conference really developed, and developed in very right way. And you see from the list of prominent speakers, and also from participants from different countries, not only Lithuanian students, but also from neighboring countries. So I wish further success to organizers. And I just wanted to tell you that our prominent speaker, Professor Gérard Mourou, today morning was inaugurated as a foreign member of Lithuanian Academy of Sciences. And this was done because he already had close relations with Laser Center. And I hope that after inaugurations, these ties will become even stronger. So with this, I wish you a very interesting lecture. I am sure it will be, and further success in your conferences. Thank you.
Thank you, Professor. We also like to ask His Magnificence, the rector of Vilnius University, Artūras Žukauskas, to say a few words as well.
Dear students, dear members of our university community, and of course our dear distinguished guests, it's a big pleasure and honor for me to greet you at this conference organized by our students. It's an amazing thing that a conference that was initially started by our even undergraduate students became well known not only within the university, within Lithuania, but also worldwide. And it's much more amazing that it's already a tradition that we, in the past, in the recent years, we have constantly a keynote presented by a Nobel Prize winner, like this time. So I just want to express my astonishment and my excitation to our students who are able to attract such speakers to their conference. And this is not so amazing if you go deeper into the tradition of our university. Our university that celebrates 440 years anniversary this year is one of the oldest universities in Europe. It is within 60 universities that survived from the 16th century. And the culture that is developed by our university is known not only in our country, but it also serves for the development of research and education worldwide, and particularly in Europe. So to finalize, I would like to wish all of you to have a nice lecture first from Professor Mourou, and then to have a very nice communication between the presenters of both verbal and poster presentations. Such conferences are very important because they implement the main mission of universities, where different people can meet, where different approaches and even different ages meet to contribute to a discussion which usually produces a novelty. The universities are developed and they are invented for the creation of future. No one knows what technologies we will have in the future, what means of communication, of medicine, of social innovations we will have in, say, 20 years, when most of you will be matured already. So research is the main instrument that makes you be active within a very unpredictable and very uncertain circumstances. And this makes you able to build the future, which is something what we do not know about. So I wish you a nice conference, nice presentations, and especially I wish to Professor Mourou to have nice listeners of your lecture. Thank you.
Thank you, Rector. And we would like to also ask the Dean of Physics Faculty, Professor Juozas Šulskus, to say a few words of wisdom as well.
So, dear guests, dear participants of the conference, dear Professor Mourou, it's a great pleasure and honor for us to meet you here at Vilnius University. It's symbolic, your lecture is a key event of the conference, because everybody knows that laser physics is one of the strongest physical fields in Lithuania. So, several words about this conference. In my study times, it was just physics faculties, students, society physical conference, and it drastically, essentially changed during last 30 years, and especially during last 10 years. Suddenly we realized that all organization of the conference are in hands of students, and their young colleagues were just helping for them. And it is, of course, it's natural change of generation, and it is a very successful change. It was. Actually, with this conference in spring, we have, in 2 weeks, we have another event concerned with physics. It is Physics Day. It's a key event not only of Vilnius University, but of Vilnius City. So we have almost half a month or even a month physics holiday every spring, and we are very happy that you are here during this holiday. So I would like to thank for organizers, for you, Professor, for coming, and as for all participants, small presents from faculty. Thank you. Thank you. Thank you. Thank you.
Thank you, Professor. Now, because this moment is historic, and I think we will never get this big audience in any of the lectures that we held in our faculties, we would like to make this moment last and to make a whole picture of the audience with our renowned guests as well. So can we just all move to this side? And we will take a picture of our all. Yeah, no, you can stay in the seats, of course. Jo, kažkur čia atsistokim. Yeah, you can stand here and.
Yeah.
Tai jis čia kur nors atsistos. Big smiles. Laser. Thank you.
Ženklelis, kurį jūs turi ne Nobelio, o Lietuvos mokslo akademijos.
Okay. You can sit a little. I will introduce you. Okay.
Okay.
Yeah. By the way, it came to my notice that the pin that Professor Gérard Mourou has now, it's not the Nobel Prize laureate pin. It's the pin of Lithuanian Academy of Science member, I think. Yeah. Yeah. Okay. Maybe his wife has it. Yeah. So also, just not to forget, I would like to thank our sponsors of this conference. Without our sponsors, neither the visit to Lithuania of Professor Mourou, neither the Open Readings conference itself would be possible. Especially, I would like to thank Light Conversion and Expla, not only for supporting Open Readings, but also supporting the professor's visit to Lithuania. So a big applause for them. Yeah, and now, if you are ready, the moment you've been waiting for. We will start the lecture of the 2018 Nobel Prize laureate, Professor Gérard Mourou. So I would like you to applaud as much as you can for him, to ask him to the stage. So.
Yes, finally. Thank you very, very much. Okay, it's very intimidating to be here. So next time, you know, when Professor Piskarkas invite me, you know, I will be very careful because I know that's a big, big thing, you know. I have to be ready for it. Well, thank you very much. I'd like to thank, of course, the president of the Lithuanian Academy of Science, Juras Banis, the rector of the Vilnius University, Professor Arturos Zukauskas. I'm sorry, you know, it's very, and these fantastic students, who organized this open reading conference, which is absolutely amazing, and Velika, you know. So I have to say that, you know, I'm really amazed to see that the students, you know, really can really put this kind of conference. In fact, I was not, can you hear me? Is it okay? Okay. When the organizer of this conference contacted me, I was not Nobel Prize. And I said, yeah, of course, you know, Algis Piskarka is a very good friend of mine. I know that this university is very, very good. So it was really a great honor for me to come here. And then I got the Nobel Prize, so it was already, you know, I was really impressed. Okay, so and I think for you also, you know, it was a coup, you know. Anyway, so very nice. I would like really also to thank my good friend Algis Piskarkas, you know, and we have been working together, or we are in contact together since 1980s, you know, almost 40 years ago, and of course during all these times, you know, the laser has tremendously evolved, and both of us contributed to really to these evolutions, laser evolutions. I have to say that you know, because of his effort, you know, the Lithuania, you know, is really on the map, really solidly on the map of the laser world, clearly, and I'm very pleased to have him as a friend. Okay, so I'm going to talk to you. I'm going basically to give you. It's not exactly my Nobel lectures, but it's relatively close. Okay, and but I'm going to tell you a little bit about my passion for extreme light. This is, and you will see that you will understand how we can really be passionate with lasers and extreme light. So here the first slide shows me with my student, Donna Strickland, who has been the third physics female Nobel Prize. Okay, and that is of course is you know, I was very pleased for that, because when the chair of the Nobel Committee gave me this famous call, you know, that you get, you know, the first week, the first Tuesday of October, it told me that I was a winner of the Nobel Prize. But of course, I was really pleased. But he told me that also I will be sharing the Nobel Prize with my former student, Donna Strickland. And I was really very pleased, because, yes, I was one of the 200 men, you know, since the existence of the Nobel Prize, you know, to have received this prestigious award. But also, I was responsible for pushing a student, you know, to get and to increase the number of women Nobel Prize, you know, by 30%. So that was nice. Okay, so anyway, so I wanted to say a few words, you know, about this event because, as I said, and I'm pleased to see so many women, you know, in the audience, and I hope that she will be encouraged by seeing that a woman, you know, can be a Nobel Prize winner. Okay, so everything started with this man. This man is Theodor Neumann, and in July, in fact, I'm sorry, in May 16, 1960, he demonstrated for the first time that light could be coherent. Okay, so we had light, you know, for 13.8 billion years, but it was only over the past 60 years now that we have coherent light. Okay, so that was, of course, a very, very important achievement. And what is amazing about light, the reason why I really like it and I'm impressed by light, is what you can do with it. And one thing we can do with light is to slow down atoms. And you can slow down atoms to, you know, very small kinetic energy, you know, counted in microelectron volt, nanoelectron volt, and so on. That is a field of called atoms, very rich field. And so that's one thing you can do, and this is very, very, very nice, of course. And the other thing you can do is you can just do the opposite. You can accelerate light, accelerate particles to the speed of light, or near the speed of light. And with the same EV photons, now you can really go to, you can, you know, accelerate particles to GeV, TeV. So we go from, what's exciting, from nano EV to TeV with light, with one EV light, one EV photons. So this is as always, you know, really impressed me with this light. You know, you can do so much. 20 orders of magnitude between really these two extremes. So now, what I'm going to talk to you, I'm going to talk to you most of the time, not all the time, but most of it is about very, very high peak power. And when we are talking about peak power, we are talking about petawatt. Petawatt, it is 1,000 times the power, the grid of the power of all power plants in the world. Okay, and it's very strange the way we do a petawatt. You say, well, oh, wow, it's amazing. I mean, how can you do that? You know, and in fact, there's a very simple trick. Okay, you know, if you know that power is equal to energy divided by time, you know, even if with a modest amount of energy, like a joule or so, you know, but if you can produce it in 1 femtosecond, that is 10 minus, I mean, a millionth of a billionth of a second, then this power is a petawatt. Okay, so you know, 1 joule is of course nothing, you know, in terms of energy. I mean, you eat every morning millions of joules. this is really, with this simple trick, you know, you can reproduce very high peak power. Now, of course, you have this is not, you may think about it, yeah, but how can you do that? Okay, and this is a little bit what I'm going to tell you about it, and yeah. So what's exciting about it? Why producing this peak power? You know, well, I mean, you can do a lot of exciting things. I will show you, but just to give you an idea, a sense of what you can do with light. For instance, with this, if you take this power, this petawatt pulses, and you squeeze it on the spot size, which is limited by the diffraction of light to 1 wavelength, which means about 1/50th of my hair in terms of thickness, you get a pressure, light pressure, enormous light pressure of, but you will have to, you will get, you know, with 10 millionths Eiffel Tower on the tip of your finger, okay? So this is very exciting because it is with light that we can produce it is with light that we can produce, I will show you, the highest pressure, the highest temperature, the highest field, the highest accelerations. So, it is a very powerful tool. Now, in order to produce this very, very high power and these high intensities, we had, of course, there is a problem, of course. And the problem is the following, is because as we amplify the pulse becomes so intense that we are burning, of course, everything on its way. And so what we had to do was, if we take a short pulse of light, okay, because as I said, you need to have energy divided by time, so the pulse has to be very short. So we take this short pulse of time. But this pulse is really, in terms of energy, at that level, is very small. Okay, it's maybe nanojoules, these kind of things. So, and now you want to amplify it, okay? And you know that if you amplify it, you are going to burn everything. So what you do is you are going to stretch the pulse by almost 1 million times. Okay, so in order to do that, you are going to use this this pair of gratings, okay? And you are going to disperse all the wavelengths which constitute, you know, this pulse. And so so you are making a very, very long pulse, And now this pulse, of course, you know, is going to have very, very million times less amplitude. And you will really amplify the pulse in the amplifier 1 million times better. And you will extract, as I said, you extract the energy 1 million times better. And you will have a very long pulse with 1 million times the energy. And now what you can do, you do the converse of what you have done, you know, at the beginning to start with. And then you get this, all the energy now, you know, into one single pulse. This energy now is represented as a very high power. So that was the trick that we used, and it's called as CPA. And you can see if you go into the laboratories, the laser research centers and and the industry conversion, light conversion, and so on, you are going to see hundreds, not hundreds, but maybe 100 of this CPA system. Okay, so now, when we came up with Donna with this idea, that was in 1985, we, in fact, a few years later, you know, Professor Piskarkas and his co-worker came up with a twist. I would call the Vilnius twist. So instead of using a conventional amplifying medium to amplify the pulse, they proposed to, and they demonstrated, but they could use what we call a parametric amplification. So this is very nice because this parametric amplification is produced only not using a very expensive amplifying media, but by simple nonlinear crystals. You know, we can do that. You have to, what we do, you have to pump it, you have to drive, and you are going to mix in this crystal two waves. One wave, which is a strong wave produced by what we call a pump, and it will be mixed by the signal, that's the short pulse that you have stretched, and then you will be able really to amplify the pulse. And we are not going to give, you know, a nonlinear optics conference here, so I won't tell, of course, I won't tell you exactly about the magic, you know, of parametric amplifications. And really, this is a very, very elegant way to do CPA, in fact. And in fact, we will really, with this technique, we will be able really to go even higher in terms of peak power, okay, than what you can do with CPA normally. So, so that's nice. As I said, you know, extreme light now, if you can do this, you know, you can really produce the highest peak power, largest temperature, largest pressure, largest acceleration, largest field. It is, in fact, the universal source of high-energy particles and radiations. As I show here, if you can take a short pulse, a petawatt pulse, and you focus it on the target, and you will get really extremely high energy electrons, high energy protons, high energy radiation like X-rays, gamma rays, and so on. And so it's a fantastic source, and that's the reason why this field is so now busy with people, and you know, very exciting field. Now, what I can really summarize why finally I'm so excited about this field is because before the laser was basically atomic physics. It was basically electron volt physics, okay? And now by amplifying these pulses, you know, to very, very high level, we can now go into the subatomic physics. We can go into particle physics, okay? So it's a fantastic bridge, in fact, between atomic and subatomic, this science. And this is a little bit what I'm going to tell you. Okay, now, this curve represents the power of laser, or more exactly the intensity, the power divided by the area. And as a function of years. So when Ted Neyman demonstrated the lasers, you know, laser was at around 10 to the 8 or so watt per square centimeter. And then we increased by using some technique which is called modular Q switching to a certain level, about 10 to the 14 watt per square centimeters. And this, you see, we have this plateau, and this plateau is really is associated with the fact that we are damaging we are damaging the material, so we cannot go higher. Then the CPA came about, and then now we could climb this curve here. We can go much, much, much higher in intensities. And here also in 1992, the Vilnius group, Professor Piskarka's group, invented demonstrated the OPCPA, and now the OPCPA certainly is going to be somewhere in the future, somewhere here. Okay, and so as we are doing that, of course, we are now, we can, the physics change, the physics of the interaction change, the properties of the interaction changes. So I'm going to describe a few examples in each category. You see that in a yellow, in a purple category, I will show you micromachining and so on, eye surgery and these kind of things. And then in a green band here, it's very exciting because you will see that the optics now, we call that becomes relativistic. That is, we can accelerate now particles to very high energy. The electron around the nucleus is now relativist. Okay. Now, if you go even higher, you go into this what we call ultra-relativistic optics, because now you can not only accelerate electrons, but you can accelerate heavy particles, protons and ions, and produce beams of protons with very, very high energy in a GeV regime. And if you go even higher, then what we can do is we can really break down vacuum. Okay. The vacuum, which is not nothingness, okay? The vacuum is really is made of particles and antiparticles, and when you reach a certain level, like 10 to the 28 watt per square centimeters, now you are going to materialize the vacuum. You break it apart in particles and antiparticles, and so you will materialize the vacuums. But it takes, of course, very high intensities to do that. Okay, so let me go to the first. The first applications, is precision micromachining. There is also some beautiful work that I've seen today using, of course, femtosecond machining, okay? And here you can see that we can really machine things with very small, in fact. I mean, we can go smaller than the wavelength of light, which is kind of surprising, but which is not. But we can you see all these features here have no basically collateral damage. Very sharp features. And that is due to the fact that as we are removing, by creating heat in the material, as we are removing the materials, the heat cannot move, okay? So you blow just the material within the skin depth, and that's it. And so you end up with very, very sharp, very beautiful sharp features. And so that is now one of the big applications, and there's a lot of very exciting work done in this university here. Now, one thing which is, of course, you can use is use these femtosecond pulses, okay? Really as a scalpel, okay? Because you can really cut biological tissue, with pristine precision, okay? And this is, of course, a very, very important application because by the way, it was discovered because I had one of my students, by adjusting, tuning the laser, got the laser in his eye. When he went to the doctors, the doctor examined the retina of my student, and he was amazed. He was amazed because he said, wow, what kind of laser do you have? And the student said, well, I have a laser, a femtosecond laser. Of course, the doctor didn't know what a femtosecond was and so on. He said, but why are you asking me these questions? Because your damage is perfect. And it's true, it was absolutely perfect. It was something with no collateral damage. If you are using longer pulse laser, like nanosecond and so on, you are going to have a crater, but with femtosecond, it's extremely sharp, okay? So, of course, that was, in fact, a great discovery. Immediately at the University of Michigan, the president said, okay, we have to push in these technologies, too important, and so on. So anyway, so we had, we made we start to apply this technology into ophthalmology. One thing that we do, I'm not going to describe all the applications of ophthalmology here, but one thing that you do is, for example, in force, if you want to change the power of your lens, of your eyes, then you would like to change the cornea flatness, the cornea curves, and what you do that by creating a flap here, you see? And it's nice, the femtosecond laser is very nice because you can focus the beam and you are going to basically create, break down the vacuum, not the vacuum, but the cornea, only where the intensity is the highest, which means at the focus. And so by scanning here, you can make very, very nice, a nice flap. Very good. Now, just to give you an idea, if you do that with a femtosecond, okay, a femtosecond laser, you can really, this is a cornea, a pig cornea, okay? And so you can really sculpt the cornea very, very precisely, okay? But if you do that, this is with 300 femtosecond, 0.3 picosecond. Now, if you are using 50 picosecond, this is the result that you are getting. You see, I mean, 50 picosecond is extremely short, right? But it's not short enough. You have to go into the femtosecond, and if you are using 50 picosecond, this is what you get. So that's the reason why now ophthalmologists, are using femtosecond lasers, okay? And in fact, there is millions. You see that here we say there's 44 million eyes operations since 2001, approximately, okay? So this is very, very big application. I'm not going to show you. So now, let's try to move to the next level, okay? And okay. Now we will actually to go. We are here, okay, with our micromachining, eye surgery, and so on. Now we would like to go into this green area. The green area, as I said, you have the electrons which moves around the nucleus. Electrons positive, negative, and nucleus positive. So it moves around the nucleus. Now, it moves at relativistic speed. The motion of the electrons at that level start to be relativistic. When you are here, the speed of the electrons around the nucleus is low. It's very low. It's hundreds of meters per second and so on. Where when you are here, this you are talking about 300,000 kilometers per second, the speed of light. Okay, so this is very much. So here the mass of the electrons is changing, and also you have what the V cross B time the magnetic field is extremely important. It's as important as the E field for the. So I'm talking to students studying optics, of course, now, and because the V cross B is going to have a push, you know, not perpendicular to the propagation direction, but along the propagation directions. So, and that's the reason why we are going to push these particles, these electrons. Here I'm going to show one, maybe the most important applications is really electrons accelerations with laser. Okay. So do I have? Oh, okay. Yes. And we are going to accelerate electrons in a very similar way than this surfer here is accelerated by a wave. Okay. So the surfer will become now our electrons. So, this technique was invented by Tajima and Dawson, Toshi Tajima in 1979, and couldn't be used without the CPA because it was. It's very simple. You take this high intensity pulse, and you focus this intensity pulse into a gas jet. You know, a gas jet about a few millimeters in dimension, you know, and of course, because the pulse, of course, is high intensity, don't forget, then you are going to ionize the medium. You are going to make a soup, which means of electrons and protons, and make a plasma. And the plasma will have a plasma wave. And this plasma wave will move at the speed of light, very close to the speed of light. So it will trap the electrons. Some of the electrons, like the surfer, will be trapped by this wave. And it will be dragged at the speed of light. Okay? And the result is you are going to have high energy beams. You know, and these high energy beams has a gradient of GeV per centimeters. You will be able really to produce electron beams with energy of GeV per centimeters. Now, you will say, big deal. What's a GeV per centimeters? Yes. Well, this is. I'm showing this is this system, which is a synchrotron Soleil on the plateau de Saclay. And this system is a 3 GeV. With the technique of Tajima, a 3 GeV fits in my hand. Okay? So you are talking about a major improvement. And of course, this was not possible. The invention occurred in 1979, and 79, and they had to wait about 10 years, okay, before they could use it in reality, because the laser was not intense, not enough to do that. So, so you see that is a fantastic, already this is a fantastic application because there is a number of applications of accelerator. You don't know about it, but you know, in the medical field and in other fields like material field, you know, and so on, accelerators are used. Accelerators are used, you know, to produce particles, produce radiation, and so on. So it's very, very important. Very, very important. So now, this big ring, in fact, represents the CERN, what we call Large Hadron Collider. This, of course, this is 100 meters below the surface, and so on. And this is to produce TeV particles. Okay, TeV particles, and now they are trying to. This is 27 kilometers, but now what they are not satisfied what they get. They are going to build one of 100 kilometers. So it is absolutely enormous. Okay, now this the conventional technology, you know, in fact, can only provide MeV per centimeters. Okay, and I show you a technology which provides GeV, that means 1,000 times MeV per centimeter. So if you apply this technique, this laser wave field acceleration technique, then you should be able really to reduce the size of these machines to about hundreds or so meters. Okay, so this is, of course, this is this here. You have if you are using the traditional technology, one MeV per centimeters, and this is this 100 meters, this football field, you know, is what you will get if you are using laser technology. But you know, you know, when you do physics, you know, it's never enough. Okay, it's never enough. You say, okay, you have 1 GeV per centimeter. Now it's good enough. You can stop here and rest on your laurel, you know. And well, no. I mean, with Toshi Tajima, we thought that we could go much higher. Okay, we found that. I mean, right now, these systems, if you want to do high energy physics or even astrophysics and so on, you have really to go into the PeV and so on, and not into the TeV. Don't stay in TeV. So, so one way to do that is really trying to transform this visible light, okay, that you are using to produce this wave field. You have to transform it into the X-ray. And this is what we want to do. What we want to do is really to take this short pulse. In fact, the short pulse here is composed about of 10 optical cycles, because the period of your period of light is about 2.5 femtoseconds. So if you have a 25 femtosecond pulse, you know, it's about 10 cycles. What we like to do is really to compress this pulse, but high energy, into a single cycle or maybe 2 cycles. We know how to do that when we have at a millijoule level, but we still don't know how to do that at the joule level. I mean, we still don't know. We discovered a way to do it. But so now what you like to do, in fact, is compress the pulse from the femtosecond regime into the attosecond regime. And if you say it's an attosecond pulse, it's synonymous to say I have an X-ray pulse. right? I mean, this is, Fourier will tell you this. So this is what we are doing, okay? And so if we do that, and I think we have a good chance to succeed, then what we can do is now you can put 1 TeV on your finger. You can get TeV per centimeter. You gain a factor of 1,000, and this factor of 1,000 comes from the fact that we move from gas to solid. But now we can, if you can produce these X-rays which can penetrate the solid, you can produce a wake field in solid, okay, and gain a factor of 3-4 order of magnitude. This is very important for physics, because but also for astrophysics, because that helps you to understand things, why this, to study particles, very high energy particles, you know, that are in fact produced at PeV level and much more, in fact. So if you can really produce that on Earth, it will be interesting. It will be really important. It will become a tool, you know, to explore, you know, what's going in the cosmos. Now, I talked about electrons, but there's also very important, you know, particles which are used, especially in medical field and so on, and these are the protons. Oh, no. Okay. Okay, so now if we can accelerate protons to the MEV, GeV field, then you can really do some serious applications. And it's very, if you have a very high intensity process, you know, when you can get this enormous pressure I showed you, about million times the Eiffel Tower on your fingers, then if you shoot these pulses on a thin film, which is in fact few nanometers of thickness, then you can really produce first, I mean, you can move the electron first because they are lightest, and they attract the proton behind or the ion behind, and you can produce, in fact, very short protons with GeV energy. But you produce these pulses very easily, and it's in a very simple way. Now, if you have to use a conventional technology, then what you have to do, this is want to have GeV, or fraction of GeV protons. This is what you have to build, okay? And that cost €1 billion, okay? And that, the dimensions is nearly 1 kilometer, okay? So now, if you can really do that with laser technology will, as I showed you, is going to reduce the size, but in enormous factors. The size, but also the cost, okay? This is what's important, and so you understand why we can be excited about these extreme light applications, because they do have an enormous potential. So one thing that you likely to do, wrong slide. No. Okay, so for instance, you are using protons. You can produce protons at very high energy. One beautiful application is proton therapy. Okay, Proton therapy for people who unfortunately have cancer. A lot of times the cancer, you know, is in the tissues, okay? But if you are using conventional therapy, you want to kill the tumors, you have to focus beams of your particle or radiations on your tumors, but you have a lot of very healthy tissue between, you know, the skin to the tumors, and you are affecting this tissue, the healthy tissue. So you don't, of course, you don't want that. And but with protons, there's, I'm not going to go into the details, but it's magic. In the protons, you can really adjust your proton beams into the tumor, which is really into the healthy tissues, without affecting the healthy tissue, the tissue which sits before the head of the tumors. And by just adjusting the energy of the proton, you can choose how deep you want to go, and where you want to put the spot size. So this is absolutely, really will be a great thing. In fact, you have, you know, proton therapy is already with us, but it's being used, utilizing conventional technology, and so you end up with extremely expensive systems. Many people got the proton therapy, and it's marvelous. It's marvelous, but the problem, what is not marvelous, is the cost, okay, and the size of the machine. So this is one, of course, of those applications that we would like really to tackle with the laser, and so proton therapy, and then you can also produce some nuclear therapy, because you can really produce some radionuclides that you are going to implant, you know, in the tumor of the patient. And then you can use it for nuclear diagnostics, and so on. So there are many good societal applications. And I think one which is absolutely extremely important, which I think it's something that we need to work on, is trying to get rid of this nuclear waste, okay? You know, of course, nuclear energy, in principle, is the best, you know? I mean, you don't produce any carbon dioxide and so on. There's only one thing, is that you are producing nuclear waste which can stay with you for a million years. And so this is not really very nice, okay? So now what you want to do is you want to take this waste and you want to bury it, you know, in somewhere and so on. It would be nice if we could change that, okay? And the way, one way to do it, which is very elegant, is by transmuting the nuclear waste, okay? At least transmuting the elements which are the most dangerous. And the most dangerous elements, that's what we call the minor actinide, okay, here. And you have four really bad guys, okay? After the rest is okay. But it's this minor actinide, neptunium, curium, and so on, which are really bad. And the way, you know, transmutation will work this way, okay? This is a working scheme, okay? There's no question about it. The only thing that we do is we do it with the laser, okay? So what we propose to do with the laser is really trying to get neutrons that we can produce okay, and we'll show you how we can produce them, okay, with the laser, of course. We need to have a proton energy at greater than the MeV, okay? And you send it to this big nucleus, you know, which compose this minor actinide. And minor actinide, they have really atomic waves of 230, and so are big compound. They have hundreds of protons, hundreds of neutrons, and so on. And what you can do with the neutrons, if the energy is high enough, you can fission the nuclei, okay? And then, so when you fission the nuclei, you end up with two smaller nuclei, okay? And but now, you know, the radionocivity now lasts only, instead of here is 2.4 million years, okay, this neptunium, for example, 2.4 million years. Now it becomes 11 minutes. 11 minutes or, you know, 21 hours, I mean, because here you have two, of course, you have different versions. So you go, I mean, it's amazing because you go from hundreds of thousand years, million years, into minutes, hours, maybe days, okay, or years, for in some cases. So, but you reduce the nocivity by a huge amount. In fact, you reduce the nocivity in times, but also in volumes, okay, by a factor of 1,000. And so now, of course, this really, okay, and by the way, I just finished the story here. When you are breaking up this nucleus into nuclei, then you can these guys can even decays to a stable state, and in a few seconds or something. So this is a very, very elegant way to do that, and this is something I would like really to invest the rest of my life doing this. Now, so I talked about nuclear waste. There's also one thing that nasty thing that we do to Mother Nature, and we are producing now zillions of orbital debris, okay? And every time since 1957, since the first Sputnik was launched, you know, you had the equivalent of 4 Eiffel Towers, okay, 30,000 tons of materials which was launched into space, and of course, and produces debris, okay. And these debris, some are very big, okay, like a washing machine, okay, but these ones are not really so much of a problem because we can detect them with radar, and when we detect them, and if we see them on a trajectory of a satellite or so, then we can move the satellite, okay? So this is, I mean, it's not ideal, but it's okay. Now, the one which are really a problem, I think, is this, a lot of these debris are small size debris. It can be centimeters, millimeters, okay. Well, you say centimeters, millimeters, you know, it's okay. Well, yeah, but you know, when you know that they go at 15 times the speed of the fastest bullet, you know, the space around you is a battlefield, you know, and soon, okay, right now, you know, it's still manageable, okay, but we spend quite a bit of money and time trying to trying to figure out ways to avoid any collisions of debris between them. So now we can manage it, but at the rate where we send satellite now, we don't send satellite one by one. We send satellite 1,000 by 1,000, okay, grapes of satellites. So it is really very serious problems. And so here, the CPA and the high intensity laser can maybe intervene, and by putting something which maybe will look like the Hubble telescope or something like this, with a lasers, which could really clean the space. In a way, I mean, it's not really that we're blowing away the debris. When you detect a debris 100 kilometers ahead, what you don't have to blow it away. What you can do is, if you can really produce just an impact, and you blow just one part of the particle, or just you blow a fraction of the particles, and then the reactions you ablate. You ablate a section of your particle, and you are getting as a result of this ablation, you are getting a rocket effect, and this rocket effect can really change the trajectory of the debris. And when the debris can really go into the atmosphere and be burned by the atmosphere, like the thousands of meteorites, which are doing the same every day, So this is the type of things that we could do. We could really, we can, and we have, of course, we have a serious program on this, and so we have to build a system. We are going to use a space station to do that at the beginning, and but it's a very serious problem. And I have to say, this is something also I'd like really it's a problem I'd like really to fix, because otherwise, if we don't do that, then we won't be able really to go to space. In 5-10 years. So this is the type of laser that we are really producing right now, working on. It's a laser which is based of optical fibers or laser fiber lasers, and it's composed of zillions of thousands of fiber lasers. And the reason why we want to do that is because we want to have a high rep rate. And if you want to have a high rep rate, that means you have to have high average power. And means high average power. If you have high average power, you have to be efficient. And you have to remove the heat. And so basically what you have to do is to augment the surface area of your laser, so you can evacuate the heat better. So that's the reason that we are using thousands. We like to use thousands, maybe 10,000 fibers, but they are phased. The difficulty, of course, they have to be phased. Okay, and if they are phased, these 1,000 fibers also act as one fiber. Okay. And that's, this is what we like to do. So this is basically the end of my talk. I really like to conclude, okay, by saying that, I'm really impressed by the number of applications of this extreme light. The fact that we can really produce this high intensity, short pulse, high intensity. There's a lot of applications. And I would like really to conclude, one of the motto of Alfred Nobel, which says that we need to do research for the benefit of humankind. And this is what I like to conclude with that by saying, in conclusion, extreme light is capable of generating the largest field, largest acceleration, the largest temperature, and the largest pressures. And it carries the best hope and opportunity for the future of science and technology. But, so I'm going to stop here, and I thank you very much for your attention. If people have questions, I don't know how we are going to do that for questions. Are they allowed to question or not? Okay, I don't know. Anyway, this is the end of my talk. Thank you very much for your attention.
Yeah, thank you very much, Professor, for sharing a passion for extreme light. Yeah, and we also have time for questions. Are there any? Oh, I see one. And
thank you, dear Professor, for an inspiring talk and for fantastic ideas for the future as well. If I may introduce myself, I'm Andrius Bernotas from Vilnius University, also I work at the Academy of Sciences. And my question is, would you see it plausible that the extreme pressures and large temperatures will allow one day to create some of the most beautiful crystals on Earth, that is diamonds from pure carbon?
I think it's possible, but on a very, very small scale. Because remember, and it can be very fast too, remember that this phenomenal pressure is indeed very, very high, but lasts femtoseconds. Okay? And the femtoseconds don't move. You know, atoms don't move. In the femtosecond, the light moves at, you know, over micrometers. Okay. You know, I don't think you will have the time really to put all your carbon atoms, you know, together. Unfortunately, I think, yeah, this is the problems, but also quality. If you think that you cannot use this light to destroy things, to kill things. There's no defense applications that I know using femtosecond laser because it's too fast. And you get the power by the time. You don't get the power by the energy. For military application, you want to get the power by the energy. We get the power by using the time, very, very short bursts of time. So this is, but you know, I think in your applications, of course, it is, I think, way too fast. You know, way too fast. But I'm not absolutely sure. Someone smart may imagine something like possible.
Thank you. Mm-hmm. We have another question.
Yes, thank you for a very nice talk. I just wondered if you could comment about these possibilities of accelerating the particles, as this is, of course, very nice in terms of obtainable energy. How about the beam?
Oh, you mean, okay.
The particle energy, yeah? How about the beam brightness? I mean, because of course you want, you know, not one proton, but a few, and or maybe a few zillions, and then that may be a problem with the laser.
You know, if you get only the energy, it's not very useful. What you want to get is a brightness. Okay, So you want to have a brightness, mean that you have a beam which has low divergence and so on. Okay, so you want to have a beam quality. And it turns out that you do with these pulses, and the reason why we do it with wave field acceleration gives you almost automatically the brightness is the fact that you do that very fast. And I mean, on regular accelerators, the reason why, because you have to keep all these electrons, charged particles together, okay? And so if you have, if the acceleration of a particle takes kilometers or hundreds of meters, they have the time to spread apart, okay? In the case of when the particles are accelerated over a femtosecond, they are accelerated over the wavelength of light, period of light. Bing, and they don't have the time to spread apart. And so the end result is you have a very, very nice emittance. You have a very low emittance. So that's a great benefit of this technique.
Another question from actually one of our guest lecturers this year, Professor Samuel.
Okay.
Thank you very much. So you raised this very interesting prospect of laser-driven transmutation of elements for dealing with nuclear waste. Now, in most situations, the number of photons we can make is very small compared with the number of atoms in a chemical reaction. So this isn't my field, but I was wondering, how many neutrons can you get after your laser-driven reaction on the sort of right-hand side of the reaction? And so is there a plausible scheme to bring this close to self-sustaining?
Absolutely, absolutely. I didn't dwell on it, okay? But what we do, in fact, we are using fusions. In fact, I can show you. So, of course, this is a very important question. I mean, you don't want to try to build something which it takes another nuclear plant, power plant, to run your transportation. So what we do is, I'm sorry. No, it's not here. Yeah, it's coming here. Okay, you see, because I don't see it much here. But what we do in order to, we need to produce the neutrons, okay? But the neutrons doesn't have to be directly produced by the laser, okay? They can be produced at relatively low, they can produce, for instance, this is here, okay? We take the lasers and we produce a deuteron beam, okay? And the deuteron beams is going to strike a tritium target, and so you are going to have fusion, and then you will have neutrons, which are going to fly apart. So, and we show that by simulations that we are really doing very well. It's a very economical thing, but in fact, you are producing the energy. It's like, yeah. So it is very, we like these schemes. We started with the other schemes where we were directly producing the protons from the lasers, just from ponderomotive force, producing the protons, but that is too expensive, okay? But here we are using the laser just to produce these deuterons and this tritium, and then making fusion between them, and that's very economical. Yeah, that's the idea. Mm-hmm.
Any more questions? We have time for one or two.
Yeah, you have to go up.
Thank you for your interesting lecture. My question is, did you try to produce two quantum entanglement?
Oh, no.
High energy pulses.
No. The temperature is way too high.
That should be theme for your second Nobel Prize.
Listen, I mean, if we redo transmutations, I don't really want a second one, tell you, because ask my wife why. You just spend your life in travelings. But anyway, but supposing that I would like to have a second Nobel Prize, and I think if you do things like transmutations, which is something very, very important, I think for humanities, that will be worth maybe a Nobel Prize. But I'm not working for Nobel Prizes. It's true. I mean, you don't want to work for a Nobel Prize, okay, because you can be disappointed, because the chance to get it is pretty small. So it's not to get a Nobel Prize that I'm doing research myself. Okay, it's not. But I'm interested about using my knowledge, and now using maybe the Nobel Prize to give me some leverage to do things for society, because right now society are very good for researcher. We like the research. We like our sandbox. And we like our tools, our toys. But we have to give back to society. We have to give back to society. And this, I think, will be one way to give back to society. Yeah.
So, and the last question.
Professor, thank you very much for marvelous, inspiring talk. I actually work in field of condensed matter physics, and we work with Bose-Einstein condensates. And I have a question whether those high energy and high intensity femtosecond or attosecond lasers would improve, in your opinion, creating condensates or something like that, because you said that with higher power, nature of interactions change, and I was wondering, what do you think about it?
Well, I mean, if you want to produce condensate, you want to be in, micro electron volt regime. What is the regime you are working on? You remember? Yeah. And we have quantum blocks containing excitons, and with photons from lasers. Yeah. So you just said it. If you have quantum wells to confine your electrons or your carriers and so on, you are talking about something which is a fraction of a eV. And so here we are talking about when you are using femtosecond laser, unless you use femtosecond pulses, but at a low energy, that is for you, which is not exactly what we want to do, what we are doing here. Okay.
Maybe the Higgs bosons could work.
Absolutely. And now we think that we could make a Higgs factory, because to produce an Higgs takes only 120 GeV, and so we are not very far from that. We are not very far. And so, yeah, this is really a possibility. It's one of the big applications, in fact.
Okay, let's thank our professor once again. On behalf of our readings committee, on behalf of our Open Readings committee, we want to say a huge thanks for you. So this is our present.
Yeah.
Thank you very much.
Thank you very much.
I think we can also together say a coherent ačiū for the professor. Let's try it. 1, 2, 3. Ačiū! Thank you.
Very good.
Yeah, so don't leave right now, please. I would like to also say that, as our rector said, this year Vilnius University celebrates its 440th birthday. And as one wise person told me, you cannot celebrate a birthday without a cake. So you all are welcomed to try a delicious cake, drink some coffee, maybe ask a question or two for the professor as well. So thank you all for attending.
Yeah, thank you.